Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and focuses on 5 key topics related to orthogonal sets of vectors. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. Let's begin by learning how orthogonal and orthonormal sets of vectors are defined. An orthogonal set of vectors is a set of vectors where all the vectors are orthogonal to each other. If the set of vectors v1, v2, and v3 is an orthogonal set of vectors, then the dot products of all the vectors in the set will be equal to 0. An orthonormal set of vectors is a set of vectors where all the vectors are orthogonal to each other and have the added requirement that their length is equal to 1. If the set of vectors v1, v2, and v3 is an orthonormal set of vectors, the dot products of all the vectors are 0, and then the lengths of all the vectors are equal to 1. Let's look at an example where we're going to determine if the following set of vectors is orthonormal. If the set is only orthogonal, what we're going to do is we're going to normalize the vectors to produce an orthonormal set of vectors. Whenever you do a problem like this, you want to begin by labeling your vectors. And I'm going to label these vectors v1, v2, and v3. The first thing we're going to do is we're going to check to see if the vectors are orthogonal. If the vectors are orthogonal, their dot products are going to equal 0. Let's start by checking if v1 and v2 are orthogonal by looking to see if their dot product is equal to 0. So we have v1 dotted with v2. This gives us 0 minus 2 plus 2. We're just multiplying corresponding components. And this is equal to 0. So v1 and v2 are orthogonal. Let's now check to see if v1 is orthogonal to v3. That dot product is equal to minus 5 plus 4 plus 1, and that's also equal to 0. Let's now check if v2 and v3 are orthogonal. This gives us a 0, a minus 2 plus 2, and that's also equal to 0. Since all 3 dot products are equal to 0, vectors v1, v2, and v3 are orthogonal. The next thing we're going to do is we're going to check to see if the vectors are orthonormal. If the vectors are orthonormal, their magnitudes are going to equal 1. Let's start by checking the magnitude of vector v1. The magnitude of the vector is just going to be the square root of each component squared. So we have 1 squared plus minus 2 squared plus another 1 squared. This gives us the square root of 6. This is not equal to 1, so vector v1 does not have a length of 1. Let's now check vector v2. This is going to be the square root of 0 plus 1 plus 4, which gives us the square root of 5, and this one also is not equal to 1. Let's now check v3. This is going to be the square root of 25 plus 4 plus 1, which is the square root of 30, and this also is not equal to 1. So our vectors are orthogonal, but they are not orthonormal. We're now going to create an orthonormal set of vectors by normalizing these vectors. We're just going to make their lengths equal to 1. Let's let u1 be normalized vector v1, so it's going to be v1 divided by the magnitude of v1. We're just taking the vector, dividing by its length to make it a vector with a length of 1. I've written our vectors over here on the right, so we can refer to them. u1 is just going to be our vector v1 divided by the square root of 6. So we have 1 divided by root 6, minus 2 divided by root 6, and then 1 divided by root 6. u2 is going to be V2 divided by the magnitude of V2. Looking up above, the magnitude of V2 is the square root of 5. So our vector is 0, 1 divided by root 5, and then 2 divided by root 5. Lastly, our vector U3 is going to be V3 divided by the magnitude of V3. The magnitude of V3 is the square root of 30. So U3 is just minus 5 divided by root 30, minus 2 divided by root 30, and then 1 divided by the square root of 30. We can now say that we have an orthonormal set, and that set is our vectors U1, U2, and U3. Let's now learn what an orthogonal basis is and how we can easily write a vector as a linear combination of vectors in an orthogonal basis. In an earlier video in this series on the dimension of a vector space, we learned about the basis of a vector space. The basis of a vector space is just a set of vectors that satisfies two properties. The first property states that the vectors need to be linearly independent. And the second property states that the vectors need to span the space. This just means that we're going to have enough vectors so that every vector in the space can be written as a linear combination of the vectors in the basis. By definition, an orthogonal set of non-zero vectors is linearly independent. Notice the word non-zero. If an orthogonal set contains the zero vector, it is not linearly independent. Since an orthogonal set of vectors is linearly independent, this set of vectors, as long as it doesn't contain the zero vector, will form an orthogonal basis for a vector space if the set has enough vectors to span the space. For example, if we have a set of orthogonal vectors in R2, the set would need to contain two vectors in order for it to span the space. And if we had a set of orthogonal vectors in R3, that set would have to contain three vectors in order to span R3. I'm now going to show you how to express a vector as a linear combination of an orthogonal set of vectors. Let's assume that our orthogonal set of non-zero vectors is U1, U2, all the way up through UP. We can then write a vector X as a linear combination of these vectors. This problem boils down to just finding C1, C2, all the way up through CP. We've done problems like this all throughout this series, and what we did to solve this problem was we would take our vectors U, augment it with our vector X, and then put it in reduced echelon form to find our C's. Now it's actually going to be easier. Since the U's are orthogonal, we can now use dot products to find the C's. Let me show you how this is done, and we'll find C1. What we're going to do is we're going to look at this equation, and we're going to take every vector in that equation, and we're going to dot it with U1. We're choosing to dot it with U1 because U1 is multiplied by C1. Every term in this equation, we're dotting with U1. Since U1 is orthogonal to U2, U3, all the way up through UP, all of these are going to be equal to 0. This just leaves these terms. We can now easily solve for C1, and we find that it's equal to x dot U1 divided by U1 dot U1. We can use the same process to find all the other C's, and we'll find that C sub I is just going to be equal to x dotted with U sub I divided by U sub I dotted with U sub I. That's a really good formula to memorize. Let's look at an example where we're given a set beta that is an orthogonal basis for R3. There's our set beta. We're going to express vector x as a linear combination of these basis vectors. Let's begin by labeling our basis vectors. I'm going to label them U1, U2, and u3. And then we'll write x as a linear combination of these vectors. Now our job is going to be to find C1, C2, and C3. We can use dot products to find the C's because U1, U2, and U3 are all orthogonal to each other. The formula for C1 is equal to x dotted with U1 divided by U1 dotted with U1. Let's go ahead and compute that. X dotted with U1 is going to be 18 plus 1 minus 8. And then U1 dotted with itself is going to be 9 plus 1 plus 1. This gives us 11 divided by 11, which is equal to 1. Now let's find C2. C2 is going to be a very similar formula, except X is going to be dotted with U2. And then in the denominator, we have U2 dotted with U2. Looking up above, x dotted with u2 is going to be minus 6 plus 2 minus 8. And then u2 dotted with itself is going to be 1 plus 4 plus 1. And this is going to be equal to minus 12 divided by 6, which is minus 2. Now let's compute C3. C3 is x dotted with u3 divided by u3 dotted with u3. And this is equal to minus 3 minus 2 minus a 56 over 2, which we're going to have to simplify. And in the denominator, we're going to have a 1/4 plus 4 plus 49 over 4. On top, we're going to have minus 5 minus a 28. And down below, let's go ahead and let's write all of our fractions as a number divided by 4. So this gives us a 1 plus 16 plus 49, all divided by 4. Up top, we have a minus 33. And in the denominator, we're going to have 50 plus 16, which is 66 divided by 4. We can divide the 33 into the 66 2 times. So this gives us a final answer of minus 4 divided by 2, which is minus 2. Let's now write down our answer. Our x is going to be equal to u1, substituting in c1 as 1, minus 2u2, minus 2u3. Let's now learn how to compute the orthogonal projection of a vector onto a line through a vector and the origin. We're going to project vector y onto vector u and label the line through this vector u and the origin as line L. We're going to call the projection of vector y onto vector u and line L y hat, and then we're also going to create a vector z that's orthogonal to y hat. If we add these vectors up, we can see that we can write vector y as vector y hat plus vector z. Y hat is the vector that we want to find. To find y hat, we're going to take the dot product of every vector in this equation with vector u, and then since y hat lies along vector u, we're going to say that we can write y hat as a multiple of u and write y hat as alpha times u. We're also going to note that vector z and vector u are orthogonal, so that dot product is going to be equal to 0. We can then write that y dotted with u is equal to alpha u dotted with u. Keep in mind that we want to find y hat, so what we need to find now is alpha. We'll solve this equation for alpha, and we find that alpha is just y dot u divided by u dot u. We're going to plug this in to this equation, and that gives us an equation for y hat. I've summarized this formula down here in the lower left. Y hat is called the projection of y onto line L, or it's also called the projection of y onto vector u, and it's just equal to y dot u divided by u dot u times vector u. Let's walk through an example where we're going to compute the orthogonal projection of a vector y onto a line through the vector u and the origin. We're given vector y and we're given vector u. I've drawn these vectors over here on the right so that we can visualize the projection of vector y onto vector u. That projection we're going to call y hat. We have a formula for y hat, and it's equal to y dotted with u divided by u dot u times u. Let's compute what this is equal to. Our y hat is equal to y dotted with u, so that's just minus 4 plus 14, multiplying the corresponding components in y and u. And then on the denominator, we have u dotted with u. That's going to give us a minus 4 times a minus 4, which is a 16, plus 2 times 2, which is 4. And then this gets multiplied by our vector u, minus 4, 2. Minus 4 plus 14 is going to be 10. 16 plus 4 is 20. And then we have our vector minus 4, 2. You can see that this is just 1/2. So we divide each component by 2 and we get minus 2, 1. The vector minus 2, 1 is the orthogonal projection of y onto vector u. Let's now learn how to decompose a vector into the sum of two orthogonal vectors. We're going to decompose y into the two orthogonal vectors y hat, that's the projection of y onto vector u, and vector z, which is the vector orthogonal to y hat. Our vector y is going to equal our vector y hat plus our vector z. Y hat is going to be y dotted with u divided by u dot u times u, and then z we can get from this formula and just solve for z, and it's going to be y minus y hat. I've summarized all these formulas in this green box below. Our y hat is the orthogonal projection of y onto line L, and it's also the orthogonal projection of y onto vector u, and it's equal to y dot u divided by u dot u times vector u. Our vector z is y minus y hat, and it's the vector orthogonal to u. I want to make a note that since y hat is equal to alpha times u, where alpha is defined as y dot u divided by u dot u, y hat is a linear combination of u, and we will sometimes call y hat the span of u. Y hat is the orthogonal projection of y onto L or u, or it's often called a vector in the span of u. Let's now look at an example where we're going to write a vector y as the sum of a vector in the span of u and a vector orthogonal to u. We're given a vector y and a vector u. I've graphed these vectors on the right so that we can visualize what's going on. We have our vector y, and we're going to project it onto the line through vector u and the origin, and that projection is going to be called y hat. I'm going to call vector z the vector that's orthogonal to u. Let's begin by writing our vector y as y hat plus z. Y hat lies in the opposite direction from vector u, so it can be thought of as a vector in the span of u, and our vector z is our vector that's orthogonal to u. Our vector y hat is equal to y dot u divided by u dot u times vector u. Let's go ahead and compute what that is. We have y hat. Now we're going to take the dot product of y and u. So that's going to be an 8 minus 21 on the top. And then u dot u is going to be 16 plus 49, and we're going to multiply this by our vector u, which is 4 minus 7. 8 minus 21 gives us a minus 13, and 16 plus 49 is equal to 65. And our vector u comes along for the ride. 13 actually goes into 65 5 times, so this is equal to minus 1/5 times 4 minus 7, and then we can write our vector y hat as minus 4/5 and then 7/5. Let's now find vector z. That's actually easier than finding y hat. We're going to go up to this equation and we're going to solve for z. So we see that z is y minus y hat. Let's now plug in for both of those vectors. We have z is equal to y, which we were given, 2, 3, minus y hat, which we just found, minus 4/5, 7/5. And this is going to be equal to 2, which we're going to write as 10/5, minus a negative 4/5, so we add 4/5. And then 3, let's write as 15 divided by 5, and we're going to subtract 7/5. Our first component is going to be 14 over 5, and then our second component is 15 minus 7, which is 8 divided by 5. We can now write our final answer. We can write our vector y as the sum of a vector in the span of u, and that's our y hat, which is minus 4/5, 7/5, plus a vector orthogonal to u, which is our vector z, and that's 14 over 5, and then 8 over 5. I always tell students that the key to this problem is knowing this formula. The last topic that we're going to learn about is how to find the orthogonal distance from a vector to a line through the origin. We want to find this distance, which is the distance from our vector y to a line L through the origin. We'll label the projection of y onto vector u as y hat, and note that we have a formula for y hat, and it's just y dotted with u divided by u dotted with u times u. This is a really good formula to memorize. The distance from our vector then to a line through the origin is just given by the magnitude of y minus y hat. Let's now look at an example where we're going to compute the distance from a vector y to a line through u and the origin. We're given y and we're given u. On the right, I've drawn these two vectors. We have vector y, and then we have vector u, and we have a line through vector u and the origin. The distance that we want to compute is this distance right here. This distance is the magnitude of the difference between y and y hat. Y hat is the projection of vector y onto vector u, and it's given by the formula y hat is equal to y dotted with u divided by u dot u times u. These are two really good formulas to memorize. In order to find the distance, we're going to have to compute y hat first. So that's y dotted with u. That's going to be a 12 plus 3, just multiplying the corresponding components. And then we dot u with itself, so each component gets squared. So we have a 16 plus 9. And then we multiply this by vector u, 4, 3. Up top, we have a 15. And in the denominator, we have a 25. And we have our vector 4, 3. If we divide 15 and 25 both by 5, we get a 3/5 times our vector 4, 3. Our first component is then 12 divided by 5, and then our second component is 9 divided by 5. Let's label this as our first step. Our second step, we'll give ourselves a little bit more room here, is going to be to compute y minus y hat. Our vector y is 3, 1, and then we're going to subtract the vector that we just computed, which was 12/5 and 9/5. Let's write 3 as 15/5, and we're going to subtract 12/5. And then 1, let's write as 5/5, and we're going to subtract 9/5. Our first component is then 3/5, and our last component is minus 4/5. One more step to go. Our third step is we're going to compute the magnitude of y minus y hat. This is going to be the square root of our first component squared. So this is 3/5 squared, plus our second component minus 4/5 squared. This is going to be the square root of 9 divided by 25 plus 16 divided by 25. Oh, look at that. We end up with the square root of 25 divided by 25, which gives us a final answer of 1. This tells us that the distance from y to the line through U in the origin is just equal to 1. Be sure to check out the next video in this series where I'll teach you more about orthogonal projections.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.